All right. Hello, everyone. So actually, let's see if I should log in as an admin to make sure we don't have hot mics.
That sounds like a splendid idea. Yes.
Let me see if I can do that because that is something, if I deal with it from the beginning, I will not regret later. Sign, sign, sign out. Okay. Sign out. And where's my credentials?
Can you also give me permission to record this on my machine?
Let me sign in, see what comes up on my cockpit. So,
Okay.
Huge. Gives me here. Good. One. All right. Now, what changed? So I can mute people now. See? Let me log in back. All right. I think yes, now I can mute hot mics.
Excellent.
So let me close this. Mm. I don't think I can give you that, but I mean the recording will come back later and then we
Okay.
continue. All right. So
All right.
started then. So welcome everyone to another OCP tap call. This is call number 102. And today we have Paul Borrill giving us a presentation about a facade of Newtonianism, network, and its consequences. So, as usual, with presenting or like introducing our speaker. So, Paul Borrill is the Chief Product Officer at Dellis, an expert on software infrastructure. He contributed to systems development at NASA, Sun Microsystems, Quantum, Veritas, and Apple. Paul co-founded the IEEE Hot Interconnect Symposium and the Storage Networking Industry Association, SNIA. So in terms of Paul's education, Paul earned a PhD in physics from University College London. He is also founder of It's About Time Club, a forum for physics, computer science, mathematicians, sorry, mathematicians, yeah, neuroscientists, philosophers, and practicing engineers to explore or unfold knowledge of the nature of time and causality. So, with no further ado, Paul, the floor is yours.
All right. Thank you. I'm going to try and share my screen. So can you see my screen okay?
Yes.
Excellent. All right. Well, thank you very much, everyone, for joining us today. Let me just put this in my screen here. So thank you, Ahmed, and thank you for inviting me. This is the second time I've given a talk here on OCP TAP. So I'm calling this one episode 2. So thank you for coming and lending me your ears for this next hour. As you heard, I'm Paul Borrill, and my background, though, is in systems architecture, software and networking in Silicon Valley, including Sun, Quantum, Veritas, and Apple. But my obsession with dependable computing started when I put an experiment on the last successful flight of the Space Shuttle Challenger. I am now on my third company, determined to realize a vision for simple, reliable, and secure infrastructures. In the first presentation, I was basically a repeat of a presentation I gave with Jonathan Gorod the previous year at a Silomar that was not recorded. This is episode 2. We intend to talk about tearing down the facade of Newtonianism and networking in particular. And you're going to hear some things in this presentation that you may not like. So I created a community, the It's About Time Club, and its follow-on, the Mulligan Stew Gang, to explore these issues of where we disconnect on between the disciplines of physics, mathematics, and computer science and engineering practice. And I encourage you to contact me afterwards if you would like to participate in that. So here's a quick overview of these talks that I've given previously. The first one was really all about is clock synchronization sufficient? And so I put everyone's mind in that distance of like, what if we launched a swarm of satellites to Proxima Centauri and they got up to 20% of the speed of light? A feasibility study has been done on this. You can do that with a gigantic laser. And how would you do clock synchronization with that? the reason, my motivation for that was to encourage first principles thinking about the nature of time and causality far removed from Earth's PAI and GPS, so that you can't latch back into thinking that we can use GPS to give us some kind of notion of global time. Today's talk is the why, and then episode 3, which will be in July, will be the how. What is it we can do to solve things? So, no, first of all, what I hope you will take away today, clocks cannot be synchronized in principle. They will therefore be problematic in practice, but they can be disseminated. And I'm distinguishing between synchronization and dissemination. Dissemination is when you broadcast something, you don't expect a reply, just like we do with radio and GPS and everything else that's talking to our wristwatches or our mobile phones. But if you want to be able to do any kind of transactional thing, you have to have a round trip. At least that's what I'm going to argue for today. And the issue is that NTP and PTP are trees. So all we need to do is be careful about how we choose the route and how, especially, that we do failover. So it's a mistake to believe that non-Newtonian physics doesn't apply because it's restricted to low relative velocities or atomic scales. And I'll get into that next. One of the things I do hope that you would take away is that monotonicity or irreversibility is in the eye of the observer. Space-time doesn't behave in a Newtonian way, and entanglement and indefinite causal order are the new paradigm in physics. In fact, 2 years ago, the Nobel Prize was won for that. This is a century after Einstein overturned Newtonianism. But because of IEEE 1588, the Precision Time Protocol, we can now measure and characterize these effects. And we can falsify Newtonianism, which has been the dominant paradigm in the development of network protocols and distributed algorithms for over 40 years. So for a wonderful description of this, I will add some references to the document by G.R.M. Morletto, which talks about the science of Kant and Kant, which is all about counterfactuals. So Newton, you've all seen this picture before. It comes from Wikipedia. So our current model of time for distributed systems has got this hidden assumption of Newtonianism behind it. And I call this a facade of Newtonianism because it pervades all of computer science and networking. We like to make believe that an inertial frame allows us to ignore Einstein's special relativity and general theory of relativity, and that quantum mechanics effects are too small to matter in our everyday lives, including the way that we construct algorithms and protocols for data centers. Nothing could be further from the truth. Quantum mechanics is not just a theory about small things. It's a theory about all things. Wonderful YouTube video by Sabine Hossenfelder you can find on YouTube. I recommend you watch that. But equivalently, we can also say that general relativity isn't just about large things and black holes. It's about the fundamental nature of space-time that we can't ignore when we think about the nature of time, even at the millimeter scale. So what I hope that you will learn today is that, number one, there is no big clock in the sky. I hope to say that enough times that someone will either object to me and argue with me, or you'll accept it. But that's one of the big learnings. So what that means is that space-time does not have a background that you can measure things against. There is no standard frequency, only a standard energy based on Planck's constant, and different observers' clocks will appear to tick, in a solid, standard frequency, for example, quartz and cesium or pendulums, but only for that observer. Clocks will experience frequency differently in different places. And finally, clock synchronization error is indistinguishable from latency. This is a wonderful insight from Professor Edward Lee of UC Berkeley that we heard in one of our Mulligan Stew meetings a few times now. So what's going on? I'm going to try and demolish the first statement here on this slide about Newton's definition of time. But I'm going to also say the second thing that Newton said, which we really like, is every action has an equal and opposite reaction. This is good. It basically says that you can't just broadcast information and expect it to be received. You have to have a round trip acknowledgement, which means that there's an equal and opposite thing going on in our protocols. If we could do that in our networks and the way that our networks are designed, I think we'd build better networks. So you've probably all seen this before in Wikipedia, but this is a wonderful animation that really kind of sets the position here that whatever way you're looking at, the velocity at the bottom, which is the speed of light, either plus 0.3 c or minus 0.5 c or 0, is going to give you a different sense of the order of events in different points in space-time. You've all learned this, if not at school, at university, and you've probably accepted that relativity is a solid theory that we haven't yet falsified in our scientific experience in the last 100 plus years now. So there is this notion of an inertial frame in special relativity, and let me explain what that is. That's true only in a frozen, empty universe. As soon as you go to general relativity and you add energy and mass, you will find that you have a dynamically evolving universe where this whole notion of an inertial frame not only doesn't make sense, it's actually completely invalid. So one of the objections here is that most people would say, these effects at the quantum scale or these effects in relativity are too small to worry about. And you can do a back of the envelope calculation to convince yourself that it's within like this thing that you might call clock synchronization error. But let me remind you, the machine code of the universe is quantum mechanical. Entanglement occurs over any arbitrary distance, and it appears to be instantaneous, at least relative to a background of synchronized clocks. So recently in the foundations of physics, we've seen renewed interest in the relationship between bipartite entanglement and the nature of time. And there's lots of really wonderful things that you will find on the YouTube and in the references that I will provide for you. But the bottom line is both general relativity and quantum mechanics are individually true in all of the experiments we've done. But we realize there's some incompatibilities that can only be resolved by either extending one theory or by replacing them both with a new theory. One of the popular ones these days is something where time and space emerge from entanglement. There's the references. So there's a great reference that just came up recently, and on the 10th of May, this was published in the Physical Review in May 24. This new theory suggests that time might be an illusion created by quantum entanglement. According to this theory, changes over time are perceived only because objects are entangled with clocks, making the universe appear static to an external observer. This challenges the traditional views from general relativity, which integrates time into the fabric of space-time, and quantum theory, which treats time as an externally imposed parameter, a constant, if you like, of something that's going on in the background. I will, the blue links, by the way, on all of my slides should all be live. If you get a copy of the slides after this presentation, click on the blue underlined links and you will find that should take you to the literature that I'm referring to. So let's get back to IEEE 1588 and the time appliance project. We can basically confirm all of our beliefs about the way that Newtonian time works and the one-way nature of time, the continuity of time, the increasing resolution of time, I guess, the difference between precision and other definitions of what we're doing in 1588. But the bottom line here is a clock is always measured relative to another clock. So whenever we talk about precision or which is something remaining stable over a long period of time, or accuracy, which is, whether something is the same as something else or close enough to it when we measure it. This is really all about measuring one clock relative to another. And you will see a talk from Pauli Erker in a few weeks' time here on this forum, where you'll learn exactly this issue, that a clock is always measured relative to another clock. So why am I interested in this? My motivation here for being on here is to find and expand on the community, which is exploring these problems in my world, which is distributed systems and data centers. So what you can see here on this slide is I'm going to introduce the games that people play in database systems and the idea of smash and restart, which is what we get when these transactions or these interactions are blocked indefinitely, and we have to unstuck them with timeouts and retries, which are from now on I will call TAR, T-A-R, timeouts and retries. So smash and restart leaves debris in the data structures in the middle of these sequences. For example, in database transactions, two-phase locking has a growing phase where transactions may acquire locks, but they can't release a lock. And then the shrinking phase where they can release locks, but they cannot acquire any new lock. And then there's a version of that which is even stricter, called strict two-phase locking, where the transaction holds all of its exclusive locks until it commits or aborts, and all the locks are released simultaneously. We'll come back to this later on. This simultaneity thing is an interesting problem in the design of protocols. Now, strict two-phase locking provides a higher degree of isolation and is simpler to implement, and it avoids the complexities of cascading aborts. But any kind of locking implies what Pat Helland in our Mulligan's Hugh gang has said many times, that locking or two-phase commit is the anti-availability protocol. And that's because it also reduces the available concurrency, or if you think about it a different way, the scalability and the performance of your database. Now, the other alternative, MVCC, allows for higher concurrency because readers do not block writers and vice versa. And so indiscriminate locks can cause contention and block other transactions, so that MVCC avoids locking for reads, but can still suffer from corruption such as write skew and inconsistencies such as phantom reads. This is the constraint we are forced to contend with in the distributed systems world when we depend upon Newtonian time. So these games are like the towers of Hanoi that you're seeing on the screen here playing out. Simple rules, nearest neighbors, create complex interactions, even over a single Ethernet link, that need to complete before the algorithm can guarantee safety. In other words, if you're halfway through your games and you only get to step number 7 and you go, whoops, timeout, smash and restart, you can imagine what happens to what will happen to these games. That's one of the things that we're going to talk about a little bit more today. So the big learning here from this slide is that if all of these steps are not completed, then data structures will be silently corrupted. And this is what we've seen for decades in the database industry. So what's wrong with timeouts and retries? The primary issue is that you can't stitch together timestamp-based systems because the beginning and the ending of an interval on one machine and the beginning and the end of an interval on another machine have no relationship to each other and will not be connected in space-time in the way that human beings think it is from Newtonian view of time. Even in an Einsteinian perspective on time can't really help you because of something called indefinite causality inherent in the uncoordinated interactions in the physics. So I'm going to talk a lot about this in the episode 3, which is coming up in July. But if you keep in mind the idea that there's stuff going down there in space-time that doesn't, you can't just add up all of the pieces of what the pings are that you think you can see on the networks and try to put timestamps on them and figure out what it is that's going on. Because there's some things going on under the hood, which is not just it stalls or stops for a while. There are some things that can genuinely go backwards, at least from a counterfactual basis. And I see that there's a chat here. Let me see if that's something I should read.
No, it's fine. It's housekeeping things.
Okay, housekeeping things. Good. All right, so let me go back to Zoom. Okay, let me continue from where I'm at. All right, so I want you to keep in mind that we're talking about the components of a computer, the networking that you all understand. You know, for example, the timelines at the top, which our poor programmers are trying to contend with when they've got multi-hundred core computers and they're trying to get, you know, the Linux kernel is trying to schedule them so that they all behave in a way that's predictable. That's a seriously bad problem. It's all stitched together with this thing that's in our mind. That timeline is not the same as the timeline that the Linux scheduler has, and it's not the same as the timeline that the NIC has, and that's not the same as the timeline that is this big clock in the sky that we're all thinking might exist here. So it turns out that you can solve this problem if you can play around with the smart NIC, and you can do things like building the PTP hierarchy where you can carefully control the causal relationships between things. And we'll talk about that in episode 3. So conclusion here, monotonicity or irreversibility of any kind is in the eye of the observer. And it's not everywhere throughout space-time. So in other words, you cannot treat things as forward in time only, because that will give you the wrong view. From a Newtonian perspective, it's incorrect, but we know that Newtonian physics is now wrong for at least 100 years. So how do we do time measurement and time management in distributed systems? So over the last, my perspective over the last 30 years about thinking about the nature of time in the design of hardware, cache, memories, hierarchies, software, distributed systems, operating systems, and networks. These, you can also think about this from an Ethernet perspective or an IP perspective or networks or mesh networks. The point is there are many clocks involved in computing that have nothing to do with time. For example, a CPU has a clock for pacing the instructions, and its timing must match that of other parts of the system, for example, the memory, but that has nothing to do with time. So I want to just distinguish those things out. Now, under normal circumstances, we would talk in this forum about PTP and about the concerns that we have. For example, we'd talk about clock drift, or we would talk about network weather, which includes all of the queuing noise that Kevin Stanton is so expert on. And it would also worry about, you know, how do we do failovers and how susceptible are our systems, not just to failures, but also vulnerabilities in security. And that's consumed a large amount of interest in this forum ever since I discovered it at the OCP conference last year and when I first met Ahmed. So the challenges here, though, go much deeper. We are going to see timeline violations even when the system is working properly. We're also going to see catastrophic disruptions during holdover, unless everything is stopped and resolved quickly because you don't want to slow the systems down. You're going to see causal violations and multiple timelines, whether it's a grandmaster clock or a GPS that's feeding it, or you know, some number of boundary clocks and ordinary clocks and all of the other wonderful, you know, definitions we have in the IEEE standard for this PTP hierarchy. All of these clocks are fighting each other if they're trying to synchronize. So it turns out, as we've all discovered, you have to disseminate instead of synchronize. And that basically means you have a tree. So when you have a tree, you have to pick your route and you have to be careful when you fail over to another route. We will talk much more about that in episode 3 in July. So this time management in distributed systems basically means that there is no big clock in the sky. So that thing, I tried to get ChatGPT or DALL-E to give me some kind of interesting, you know, image here to talk about a rainbow above the distributed systems, and it came up with this. I thought it was cute, but the point I wanted to make is that there is no big clock in the sky, and that thing that is ephemeral that we're trying to synchronize against doesn't exist. In fact, here's my animation that I spent hours on trying to get right. There is no big clock in the sky. I finally got an image from DAL-E that kind of like depicted what I wanted to say. The bottom line from this picture here is that we cannot synchronize time to an imaginary, inaccessible timeline. The universe doesn't work that way. So I'm going to use my new animation that I also produced recently. There are many aspects to the physics which thwart our attempts to synchronize clocks in the way that we expect the Time Appliance Project will explore. And we can explore some of those today and in the next episode 3. So my motivation is the world of distributed systems. So what I'm trying to persuade distributed systems programmers is time doesn't flow like this. So you can see on my screen here, you can see that both of these entities, Alice and Bob, if you want to call them, they don't have a background of time that's going in the same direction. So for example, I'm going to make the assertion that a ticking clock on one computer does not imply the forward evolution of time on another computer. And this I call a directionality assumption. And we can basically test for directionality violations now that we have PTP. 1 nanosecond clocks is, in fact, even 1 microsecond clocks is good enough to detect in some of the timestamp data that time does not work that way. I'm calling that a directionality violations. But there are other violations. There are the smoothness violations. In other words, the one thing smoothly connected to another, it doesn't work because of quantum mechanics. And that in turn is going to give you causal violations, which you will see in distributed systems programs. Once we realize that that is kind of the problem we're dealing with, well, we're all engineers. We can tell us a problem is impossible and we'll engineer a way around it as long as we understand the problem correctly. So what we think is that these violations in directionality and smoothness and causality are observable in the PTP hierarchy. And that means that we have to accept or tell our distributed systems programmers that they can't expect to use timestamps as an ordering construct. Timestamps are an unsafe ordering construct unless you do something else to overcome some of these violations that you will see in space-time. And finally, you're going to see lost, uncorrupted data, which is where I'm concerned, where everyone who does a database system is concerned, and where the whole, cloud industry has been battling with now for at least 10 or 15 years to try to build things that avoid these trade-offs between performance and safety of the data. I call this the facade of Newtonianism. And actually, that's really a term that came from Pat Helland. I want to acknowledge him for coming up with these wonderful statements that really provide simple and clear descriptions of the kinds of problems we're looking at. Another way of looking at this problem is some of the published literature. And I've seen a lot of literature in the physics community, which I'm familiar with, but you might find it much easier to look at a piece of data that came from the computer science community. This is a Stanford experiment called Huygens, where they used measurements of nanosecond clocks in the NICs to be able to understand what's going on. You'll notice that the clock here, there's a video link here. The paper is linked in there you go. The video is linked here. The paper is can be clicked on here. But what's going on over here, you'll notice that some of these have got green spots. And some of them got blue spots. But what really is going on here is this difference between here and here, which is, by the way, about 1.5 microseconds, which is 1,500 nanoseconds. That's more than 1,000 times bigger than the error that you would expect from a space-time interval because of the limit of the speed of light. You can't go faster than the speed of light. And what you're seeing on this picture here is something where packets are received before they were sent. At least that's what it looks like. So the question, is this faster than the speed of light? Is it a mistake by the experimenters? Did, for example, the experimenters add in the internal computation time as Kevin Stanton would encourage you to do? So one of the things I do notice, though, in this paper, after having read it in depth when it first came out, is that they're manipulating their data with something called support vector machines, which is a classifier that assumes hyperplanes. In other words, it assumes there's hyperplanes there, and it calls anything that's not on that assumption, false data, and it drops it. Bad idea. I don't know of any experimental physicist who dares to drop real data, because usually that's where interesting new physics comes from, or at least interesting new computer science in this case. So the interesting question is how variable or deterministic is the transfer time over PCIe. This is what Kevin calls the last few centimeters, or I think the last thing it used to call it the last inch, and now they call it the last 2.5 centimeters. I love that. And it's great. Or the question I want to leave you with in your mind is, or might this be something else that we're not really looking at properly? And just taking a look at these packets that were received before they were sent, and this gap that you see here, and especially, this thing at the top here, whoops, let me go back one. This green dots here, these are well past the error bars of anything that you would expect, I think. And as you can see that the space-time interval between the blue and the green, the Alice and the Bob, is basically the packet being sent is time-stamped by the NIC, packet being received, time-stamped by the NIC again, before it's then given to the software and then processed through Linux and then the application. We can always take a look at the experimental evidence and say, no, all that stuff in the middle must be wrong. Let's go back to a Newtonian way of thinking. And that's what they do in these pictures here. They basically go from the top where they've got all these anomalies, and they use support vector machines and say, anything that is not within this band, we'll just forget. We'll just pretend it doesn't exist. So I encourage you to take a look at that. I'd like to show you where this intuition goes, though, because it's not necessarily bad. Kevin Stanton even challenged me to the notions that computer scientists have when they go through this kind of understanding. So I'm going to talk right now about the conveyor belt metaphor. And Kevin has been a fantastic help in connecting, the world of that he knows so well in PTM and time measurement and IEEE 1588, of which he is an expert, and this ongoing unfolding of knowledge that we have between physics and computer science that the database and distributed systems community can benefit from. So the three ways of looking at the conveyor belt metaphor. The first is obviously Newtonian, the one we're looking at right now, where time is absolute. The speed of light is instantaneous, therefore infinite speed of light. It flows uniformly, like those pictures of those two rainbows going forwards earlier on, a couple of slides ago. And more importantly, it's going in the same direction. Everything that we receive as a human being is going to give us this sense of monotonicity or irreversibility. And that's why a lot of our intuitions about the way physics works is often wrong. The second one is a relativistic one, which is really interesting because relativity alone doesn't give you a kind of like break you out of the convincing you that Newtonianism must be wrong, let's abandon it altogether. There is still this kind of sense that you could have all of these parallel conveyor belts going on where time is relative. Of course, some of the conveyor belts are going slower and some are going faster. It's not hard to think in terms of, these variable speed conveyor belts, depending upon, either the relative velocities between things or, how deep you are in a gravitational well. It also gives you a sense and intuition of going in the same direction. It's easy to see that a conveyor belt can only go forwards. Sometimes it can go slower, even really, really slow when it's near a black hole, or it can go a lot faster, when we're, all the way up to the speed of light, depending upon how much energy you have to give momentum to your spacecraft. So it's really easy in a relativistic point of view to believe in the conveyor belt model. When we get to quantum mechanics, though, all bets are off. First of all, we've got two very nasty things going on. One of them is that there is this idea of instant correlations, that Bell state measurements, quantum entanglement occurs over any arbitrary distance. The second thing we have is that you can't measure that or know what's going on unless you have a speed of light measurement. In other words, you actually have a round trip between the sender and the receiver, and then you can do signaling to say, this is what I did on my experiment, what did you do on your experiment? You compare the two, and it looks like it's instantaneous. But there's something else going on. What we know from some recent work by Kaslav Rukner at the University of Vienna, which has now been decisively demonstrated in an experiment by Julia Rubino and her friends at NIST, this thing called indefinite causal order. And so what we've realized is that the one thing that's different between the same direction and the same direction between Newtonian and relativistic world views is the quantum is basically going to say, hang on a minute, it's not just this Heisenberg uncertainty between energy and time, which we're all familiar with, less than or equal to h bar. No, it's actually deeper than that. What's going on is you can actually genuinely get indefinite causal order using something called a Wigner's friend experiment, and you can get superposition in time. And this kind of an oh shit moment when you realize that, because it's like, well, if that's true, we can also engineer around it too. So this indefinite direction is something that really messes us up. And now we can finally throw out the assumptions about Newtonianism. So let me introduce you to the basic idea here, the central theme of this talk, which is the way we think and the way that Newtonianism makes us think is forward in time only. And I'm going to call that phyto. So whenever I use the word phyto, this is what I mean. And what I'm trying to say here is that time is not irreversible. It's not continuous, probably. I'm not certain about that. We have lots of disagreements in some of the scientific communities. But it's certainly not monotonic, which is what you would expect it to be in the applications process space for an x86 processor, for example. So observers experience phyto. Holdover in the PTP hierarchy is phyto. Logical time in a Lamport sense is phyto. There is nothing in Leslie Lamport's vocabulary that has the word reversibility. This is why TLA plus is so incredibly hard to reason about, because it gives you only the forward in time kind of way of thinking about something. It doesn't give you a true picture of reversibility for us to think about time differently. And this is true in Leslie's most recent book, by the way, that he put on the archive a couple of months ago. So logical time is phyto. Logical monotonicity, which the folks at UC Berkeley are very fond of, and the folks at UC Santa Cruz, that is also phyto. So what are the takeaways? Time is not continuous. Measurement is discrete, even in a quantum clock. And you will find that in the conversation with Pauli Oecker, who's talking here on this forum next month. Time is a complex integer. It's not a monotonic timeline. And when you think of it as a complex integer, the Gaussian integers, I think it's called, then all of a sudden you think you've got more space in your mind and more counterfactuals you can think of about how we can manage these protocols. And time is not unidirectional. Directionality is stochastic. It's not just you got stochastic on a Newtonian line of time from minus infinity to plus infinity, and the stochasticity is like bouncing backwards and forwards around what we call the present. No, the actual direction of time itself at the very core of space-time appears to be stochastic, until of course you build up some kind of information model where it turns into energy and matter, and then eventually matter and rocks and human beings, and inventing things like the PTP protocol. And just before you all, tell me about well, this is the way we solve this. I've got some bad news for you. Retries don't work, and they will just destroy your sense of temporal intimacy when you try to do transactions. In other words, you can't use timestamps on a single Newtonian line to construct a transaction. That assumption will blow up, and you will see that in the violations of the test, especially when you have nanosecond clocks available and you can actually use tools like lingua franca, for example, which has a built-in model in the software to be able to deal with reactors instead of actors. We'll talk a little bit about that in episode 3. So this retry orchestration will not save you. But notice this. There is a FITO statement right in the middle of this thing. It's called a strict happen before relationship. And this happen before relationship actually is foundational in Leslie Lamport's way of thinking about things. But here's the issue. Happen before is meaningless unless it's intimately associated with happened where. And Leslie agrees with this, by the way. I gave a talk on time clocks and the reordering of events in 2016 at the GitHub headquarters, and I was delighted and honored to have Leslie Lamport there in the audience, and he and I talked a few times afterwards, and he agrees with that statement. You have to tie the when and the where together, because separating them will mislead you. So one possibility, though, which is I'm going to torment you with between now and the episode 3, which I'll show you in July, is that one possibility is that if you can create logical simultaneity, or what one of the papers has called happened simultaneously, then it turns out that you can actually solve this particular ordering of time problem and deal with the are you going forwards? Are you going backwards? Ancilla that you need to control the forwards and backwards operation of these protocols. But in the database, that requires blocking, and no one likes to block. So it's 11:43 right now. I want to try and finish up quickly and get to the questions. So you're going to see Paolo Urca in a few weeks from now answer the question: is a qubit a clock? Is a single atom a clock? Is a single ion a clock? And the answer is no. And he's going to show you why. And in a similar flavor, I am going to say, is time simultaneous? Is there a big clock in the sky? Can clocks be synchronized? And I'm going to say no. And I've given you some of the reasons today. I'm happy to go into the physics in a deep dive, as deep as you'd like to go. But the problem that this creates is maintaining liveness with timeouts and retries. And conventional networks and protocol stacks use these timeouts and retries to maintain liveness. This makes exactly one semantics impossible. This also leads to retry storms, which is a cascade failure. We see a great deal in data centers where the whole networks are melting down and you have to restart things, or you have to go back and tune all of your timeouts. And what this does, though, unfortunately, is it creates this silent loss and corruption of data structures. And this is a problem that we've seen in distributed database for decades. Synchronized time won't save you. Here's Kafka. Timeout causes data loss. Here is the folks from the University of Waterloo who did this wonderful paper, 2 of them now, one in 2019 and another one in last year, 2023, where they talked about network faults leading to transaction failure. And this is called, the link for the first paper is down here, the link for the second paper is up here. And I've left that just as 3 letters because I want to embed that on your mind. It's called partial network partitioning, or PNP. Partial network partitioning is one of the things that you can use as a test to see if your data structures are being corrupted. And the answer is yes, they are. Every one of those distributed databases and distributed applications on here show catastrophic failures, which stay hidden even after the partial network failure has been healed. You'll also be familiar with something which is a major issue for transactions, which this isn't just latency, it's the worst case or the long tail latency. So on today's networks, dropped and delayed packets lead to retry storms, and those retries interfere with other traffic, leading to yet more dropped and delayed packets. We are looking at that. We believe you can't solve this problem, or we'd like to try to explore if we can solve this problem with synchronized time. So the ghost in the data center, finishing up right now. There are many inexplicable behaviors in today's data centers, and conventional distributed systems confound us when we try to understand and characterize their concurrent behaviors. We assert this is because of the misapplication of the Newtonian time assumption in our algorithms, protocols, and especially in our reasoning about the mitigation of failures. So it's clear right now the distributed systems confounders, common knowledge is the issue that distributed systems programmers are familiar with. You can't do that without request reply interactions. And the 2022 Nobel Prize was won on this idea of correlations appear instantaneously over any arbitrary distance, but signaling requires the speed of light. I'm going to leave you with this statement right now as the last item on my slide. I'm actually up to slide 25. I have 30, but this is the one I'd like to stop on. And the line I'd like to stop on, space-time, it appears, has a handshake. Okay, well, thank you, gentlemen and ladies. I thank you for listening to me. I hope that was an intriguing conversation, and I'm happy to open up the floor for questions now.
Wonderful. Thank you very much. All right, so let's go for a question. Hisham?
Yeah, so very good presentation, Paul. What do you think of Eric Brewer cap theorem?
What do I think of what?
Eric Brewer, the professor in
Eric Brewer, yes. Eric and I had a conversation about the cap theorem when I was looking at acquiring his company. I was an executive at Veritas Software. We were looking at acquiring Inktomi, and we had a conversation a long time ago right there where he told me about he had this idea, where you can have this trade-off between consistency, availability, and partitioning because of the pervasiveness of failures in networks even then. And I talked to him and I said, Eric, that won't work, right? And he said, well, there are some challenges in thinking about it from a relativistic point of view. He doesn't know anything about quantum mechanics, but he said, Paul, here's why this is a contribution, this cap theorem. He said, it's such a complex, difficult to think about problem. Ordinary programmers, they need to handle something to reason about, something that they can at least make all of their software, 99% better, maybe not getting to 100% perfection. But the idea of the cap theorem was useful. Now, of course, we've since found out that there's a big difference in the definition of consistency that's used in the cap theorem and the definition of consistency that's used in the ACID properties in databases. And that's been widely debated in the community. So I have a huge respect for Eric. I think he did some great work, but ultimately I think he was wrong.
So can I ask one more question, Ahmed? Or
Yeah, good.
Yeah, so Paul, since we met, I have been asking this question. Given all these link layer protocols that we are familiar with, or even layer 4 like TCP, where they rely on handshaking and they establish reliability by sending acknowledgement, right? I send you something, you acknowledge you received it. When I look at your presentation, sounds like that is not the right way of establishing reliability. It's correct?
Well, I think about reliability differently. One of the things that we're taught when we distributed systems programmers is we're taught to use more redundancy, either spatial redundancy or temporal redundancy. We're all familiar with doing that in coding and network theory and in the way that we do distributed storage, for example. This was one of the big issues at the Storage Networking Industry Association 25 years ago when we were putting together the technical committees. But this idea of more nines is an old-fashioned concept. And there's a wonderful paper by the folks at Google that says that nines are not enough. And so what I think we have to do is we have to go into the deeper notion of what we mean by determinism. And we've had many discussions about this in the Mulligan Stew meetings. And one of my favorite definitions is the one that Edward Lee comes up with, which is really all of these ideas of determinism and reliability is all about the model. It's not about the physical reality that we're trying to explain in our mathematics, in our protocols, and our formal verification. So when you realize that determinism is a function of the model, you realize that you can say, well, hang on a minute, we're engineers. We can invent a new way of thinking about this, and I call it determinism on demand. So instead of having something that is only 99.9 reliable, with more and more redundancy, that's more and more expensive, I say, no, if you think about this differently, especially if you have reversible protocols, this counterfactual thinking, you can actually build something where you get to know immediately whether that transaction succeeded or whether it failed. You don't get a guarantee that it failed. You get a guarantee that you'll know. That is determinism on demand. Did I answer your question?
Yes.
Okay, anyone else on the floor who wants to ask a question?
Bijan, do you want to ask about the pulsar? I mean, I think again, Bijan has it like in the comments, like it's like wondering. I mean, pulsar.
Okay,
Yeah.
sorry, I was on mute. So, I was just kind of teasing, but you had that beautiful slide with the rainbow, and it said there's no such thing as a clock in the sky. And I said, wait a minute, what about a pulsar? Because within a pulsar is observable within a single frame of reference, and coincidentally, time is consistent within a single frame of reference. So wouldn't a pulsar be a clock in the sky?
That's a really great question, Bijan. Thank you for asking that. But think of it this way. A pulsar is a root of a space-time set of ordering, and you can have many pulsars. And so think of a pulsar as being like a grandmaster clock. So just like you can pick any different pulsar and watch them with our instruments and define what their periodicity is, you can do the same with a grandmaster clock. So it's a great question, and it also illuminates why you have to pick your root. You have to pick the thing that you trust as your timing reference. And that goes all the way down to the lowest atomic molecular levels when we're building atomic clocks. Did I answer?
To elaborate on it, I think like basically there is no big clock in the sky. Like there is a lot of emphasis around the big, and big means like there is no hierarchy or superiority that you say, okay, this is the ultimate clock as a definition, and then you can go with like, I mean, either you go with let's say a pulsar to get your frequency set, or you go with a very long interferometry to get your phase, which we use actually to get the leap second thing. These are arbitrary, and like basically I think again, that's what I'm understanding. The essence, what you have there is there is no physical definition that de facto this is time, except like if you trace it back from energy, and energy go back to, let's say, Planck energy packets. Anything else is just an arbitrary thing that you choose to have it now aligned to a pulsar or aligned to this man-made constellation, which appears also in the sky, GNSS, or like any other things like that. Does that make sense? I think that's what you were trying to elude.
That's correct.
Yeah, and the reason why I was joking around with pulsars, because if you think of I think of time in terms of space-time, and I think of pulsar being a gravitational distribution of energy, then this is a very essence of time, right? Is the space-time.
All right.
is I remember one of the things that was on the plaque that on Voyager that was sent out to the edge of the solar system was this wonderful pictorial depiction of like distances between different pulsars, and in there was encoded the numeric periodicity of those pulsars, so that if some alien civilization in the future discovered Voyager, it would be able to say, oh, if we decode this, we can see where they were approximately in the universe based on these extremely stable pulsars. So I thought that
Terrible
was
idea. Terrible idea.
but we only know that in hindsight.
All right, Bilal, do you want to like explain a little bit on your comment, or are you good? Yeah.
It was a command. If there is need to describe further, I could.
I mean, sure, you can
It's
probably start. Yeah.
It's basically about when we timestamp a time packet that is actually sent at the time that we timestamp is not the real time that is sent out, because at the end, when this packet is put on the wire, there will be still a time passing, and system will not be 100% deterministic there. Therefore, in send side and on the receive side, there will be always an error factor. And if it is not calculated and considered correct in the measurements, then there will be negative values, which is going to be observed as the packets received before it was sent. So it's a calculation error, basically.
Yeah. Wonderful. Judith, do you want to explain? Like, I mean,
I think we touched on my question. So I was just wondering, like, there's no big clock in the sky in the present, but can you treat, a fake paper timescale in the past effectively like that, where, all the events have occurred, so you can know the causality to have that determinism. And even if you've got like, different levels of time, you can still have some transfer function that gets you from the past UTC to present. So, or is there something flawed in that thinking?
Well, there's nothing flawed in that, but what it does, it exposes the multi levels of abstraction that we use to describe different layers of understanding as human beings in what the universe is giving us. So down at the quantum level, there is absolutely no difference between forwards and backwards in time, and the uncertainty now is well understood as an alternating kind of uncertainty. When it comes to general relativity, for example, we used to think that, well, that doesn't matter. It's only about, big bangs and black holes and that kind of thing. And it turns out, no, we can actually now, as you probably know well, Judith, because you're in this world, you can now do time measurements using optical clocks to get down to the millimeter level to measure differences in gravitational field. And these experiments are now well established and quite recent, but astonishingly good engineering from my perspective. You're the better expert on these. These
June's work is amazing. Cool, thank you. I appreciate it.
all right, we're on top of the hour.
All right, for everyone, if you're interested, I will put this up at the end. There is a website. We're actually getting a lot more of the talks orchestrated up there right now. We have a couple of people helping us do that. That's called It's About Time Club. So take a look at what's going on there. We've been for 2 or 3 years. We've been putting up some great podcasts from some really excellent physicists and mathematicians. And what we did though is last July, almost a year ago, we hit the pause button on that. And one of the reasons was because it was getting too popular. On the Clubhouse, we were getting something like 2,000 people showing up, and there was a huge burden there for curating all that material. I did not have the administrative or the infrastructure support to be able to continue that. So what I did was I transitioned that to a private weekly Zoom meetings, which is by invitation only. And so you really have to be providing some advantage to us or some benefit to us in order to be able to be invited. I've had a few people being in who want to be invited. And I usually ask the rest of the Mulligan Stew gang before I bring them in. And one or two people have been rejected, but most people have been accepted. But I'd like to try and keep those meetings small. The numbers of people we have on the screen today, I don't know, 5 by 5, that's 25. So if I have 2 screens worth, there's 50 people in the meeting today. That's way too big to having these discussions. But anyway, please feel free to email me at this email address if you think that you can contribute constructively to these conversations. And beware, we encourage constructive conflict. In other words, we don't think that you can be polite in these meetings and actually each of us learn something new. So that's why we keep the recordings and transcripts private. Occasionally, we'll put some of them on and edit them when we get more resources. If you want to offer your time as a curator, as a transcriptor, as a file management, video management kind of person, then that would be a contribution that we might welcome.
Do you need a timekeeper?
I'm pretty good at that, as Ahmed has discovered on the Friday morning meetings.
Yes.
My CEO at Sun Microsystems taught me to always close your meetings down on time. So speaking of which, it is now 2 minutes past the top of the hour.
Yes. All right. So thank you again, Paul, for the great presentation. And there will be, I think, in 4 weeks, the other one, if I'm not missing, or 6. I don't know. Like, just check what's on the wiki. However, the next one in 2 weeks is going to be at 8 a.m. Pacific time, meaning this is 11 Pacific time. So just like, again, since we have people from Europe and everything, so basically 3 hours earlier, because we're trying to accommodate the presenter, which she's presenting from China Mobile. So yeah, and then we'll see, like, time to time, you probably need to do this. Like, either we throw it a little bit this way or that way. That's not my fault that the Earth is a sphere, and there is always someone that gets screwed, like in different region, but it is what it is. So so we'll see you guys in 2 weeks at 8 a.m. All right. Bye, everyone.
Thank you, everyone, for listening.
Thank you. Bye-bye.